We begin this section with the question, how many ways are there to line up 5 students? Using decision algorithm, we can see that step 1 would be to choose the first student. And since there are 5 students we want to line up, there are 5 options. Next, we'd have to choose the person that's second in line. And since we can't choose the person that's already in first, there are only 4 students that remain. For our third, we'd have to choose the person that's in third. At this point, there are only 3 students left to choose from. For the person that's in fourth place, we'd only have 2. And by the time we've lined up 4 of the 5 students, there's only 1 student that remains. Because these are steps, we would multiply them all together to get 5 times 4 times 3 times 2 times 1, which in this case is 240. So our next question would be, how does this change as the number of students to line up changes? And we could ask, what if there were 10 students? In this case, if we followed that same algorithm as before, we'd get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And because this is a handful, we introduce our new operation called factorial. And we denote that we're taking factorial of some number with this exclamation point. And in general, we'll say that the number of ways to arrange k objects, n objects, is n factorial. And symbolically, n factorial is n times n minus 1 times n minus 2, all the way down till 2 times 1. Now I'll also note that 0 factorial is defined to be equal to 1. In this previous example, each way of lining up the students is called a permutation. And we'll say that the number of n-long permutation of n elements is n factorial. However, in general, these n-long permutations and of n elements don't have to be the same number. So imagine we had 10 students and we only wanted to line up 5 of them. Well, here we can use the similar logic of how we set up the first decision algorithm to say that the number of options for who's in first in line is 10, the number of options for who's second in line is 9, third in line 8, fourth in line 7, and fifth in line 6. We can count there's 1, 2, 3, 4, 5 students in this imaginary counted out line. What we did was we started at 10 and counted down, and so we had 5 in the list. And in general, that's going to be exactly our formula for the number of k-long permutations of n elements. So if there are n elements, the number of k-long permutations, which we'll symbolize with p of n comma k, is equal to n times n minus 1 times n minus 2, and on until n minus k minus 1. But the important part is that there are k numbers being multiplied. If we wanted to more concisely express this formula, we can say n factorial over n minus k factorial. As an example, let's imagine an album that contained 13 tracks and that you wanted to make a playlist of 8 songs. And let's suppose we don't want to repeat any of them. Our question is, how many such playlists can be made? Because playlists have an inherent order, this is the same as the question about lining up students. So here we have 13 tracks and we want to order 8 of them. In the language of permutations, this will be 13 permute 8. Using one of our definitions of this function, we can say this is 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6. How do we know to stop here? Well, we stop at 6 because we have 1, 2, 3, 4, 5, 6, 7, 8 terms in our product. Or we can use our formula, which says 13 factorial over 13 minus 8 factorial. 13 minus 8 is 5, so this is 13 factorial over 5 factorial, which is 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 5 times 4 times 3 times 2 times 1, and we'll notice that these last 5 terms canceled out, and we end up with the exact same as before, 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6. As our final answer, we get that there are 51,891,840 ways to make an 8-long playlist from a set of 13 songs.